Today's objective is objective 128. Students will be able to translate words into algebraic expressions and equations. Before we get into that, we are going to do a little bit of a review. We're going to use problems 1 through 4 to answer part A, B, and A, B. So an algebraic expression is exactly what you see here. It is a math sentence using numbers, variables, and operations. Now, a constant term, it is a number that stands alone, meaning has no variable being multiplied or divided with it. For example, part AA is BA is asking what are the constant terms in problem 2. Looking over here, I'm going to go ahead and separate my terms. This first term is 3x. There is a variable standing with it, with the 3, so this is not a constant because it does have x being multiplied to 3. However, if you look at 8, 8 is standing alone. There is no multiplication or division with any variable. So 8 is the constant in example 2. What are the constant terms in number 3? Pause the video and see if you can figure it out before we give you the solutions. So in number 3, the number that is standing alone or not being multiplied or divided by a variable is -4. Hopefully that is what you also got. All right. Next, the coefficients. Try to fill this out on your own before we provide it for you. So take a moment to pause, write down the definition. What are the coefficients in number 3? We've written down 1 through 4 down here because our screen can't hold it. And the coefficients in number 4. So the coefficient, by definition, is the number that is in front of the variable. Now, we know that it is the number that's being multiplied with the variable. Some easier examples include 3x, right? We can easily see that 3 is sitting in front of x. It's also being multiplied by x. This tells you that we have 3 x's. Now, a more challenging example is 3x divided by 4. Now, here, the coefficient was 3, but here, the coefficient appears to be 3, but we know better than that. If this is asking us how many x's there are, the coefficient tells us there are 3/4, because we're going to multiply x by 3 and then divide by 4. So we can rewrite that as a number in front of the variable as 3/4 x. All right, what are the coefficients in number 4? We've again rewritten them down here. Looking here, I'm going to separate each of my terms. The coefficient for the x cubed term is 2. The coefficient for the x term is 8. And notice, 4 has no association with multiplication or division with a variable. Therefore, it is not a coefficient, but it is a constant. Whoops, I totally forgot to do letter A. Thanks for the reminder, Mr. Riggs. So it says, what are the coefficients in number 3? So sorry, I skipped ahead. Well, in number 3, we've already established that -4 is a constant. And looking at this x right here, we have to think, is there a value that's being multiplied to x? Or do we know how many x's are here? Well, if we put in our hidden 1, we can clearly see that there is 1x in this expression. So the coefficient for this problem is positive 1.
We're on part B here. The word product, hopefully we know by now that that means to multiply. You can also think of it as the result of multiplication. Now, we oftentimes see this word come up with word problems. When you read the product of, that's giving you a sign that you're going to multiply whatever comes next. So let's say the product of a number and 3. That's saying 3 times that number. That's saying multiply those two values together. So be aware as we start to use that, and it's subjective. Also, when thinking about product, sometimes students confuse this with power. If you read a word problem that was saying, to double a value or triple that value, that's still talking about product. Like if you read the phrase, triple some number, that's saying you have some number, and now you're doing 3 times that value. That phrase still implies the same idea as product. You're still multiplying. If it were going to be a power, it would have to say some number times itself 3 times. It would be very clear that you're using an exponential rule. But it's just saying triple some number, so we could represent that as 3x, which is saying 3 times x. That's all under the umbrella of the idea of what is a product. On letter E here, you see the word power. The first thing I'm going to write is or exponent. We're not sure which word you're more familiar with, but they both mean the exact same thing. What a power or an exponent is telling you is it's the number of times a value multiplies itself. So that's what power or exponent actually mean. The number of times a value multiplied itself. A really easy example that you're really familiar with. Let's say we had 4 squared. That's actually saying 4 times 4. It's saying 4 multiplied by itself just 2 times, which gives us 16. We're going to explore a few more examples down here below. Let's say we had 3 raised to the 0. Now notice the words I just said. We can say this in 2 ways. We can say 3 to the 0 power. We can say 3 to the 0 power. Or we can say 3 raised to the 0. We can also say 3 raised to the power of 0. Now the true meaning, this is a really important key point that you might not have known before. Anything raised to the 0, no matter what the value is, equals 1. Forever and always. It's a math rule that you should memorize. Even if I had like 27x and that whole thing was raised to the 0, that resulting value is still 1. Anything that's raised to the 0 has the value of 1. Now as we go along, now we have 3 to the first, so again we can represent that as 3 to the first. Notice how right here, I don't include the word power. It's a little bit of personal choice. You could say 3 to the first power. We could also say 3 raised to the power of 1. That'd be 3 to the first. Now this is saying, the true meaning numerically is 3. Because it's saying 3 multiplied by itself, but it's just saying 1 3. You basically just have 1 3 available. So that's just the value of 3. Now we get into a little more unique wording. If we have 3 with an exponent of 2, we can say it as 3 raised to the second power. You can say 3 raised to the second. You might also have heard it as, I'll put it right here below in quotes, 3 squared. That's a really important vocabulary word. Whenever you see a power of 2, mathematically you can also refer to it as that value squared. So we can say this as 3 squared, or 3 raised to the second power. Now when we get into meaning, I'm actually going to write this out. This is saying 3 times itself 2 times. So we have 3 times 3. So the true meaning is actually 9. Because that's what 3 squared means. 3 times itself 2 times. Last one we're going to show for you, and then you're going to fill out 3 to the 4th, and also 3 to the 5th. The last one that's a little unique with the wording is 3 with an exponent of 3. So we could say this as 3 raised to the 3rd. You could also say 3 raised to the 3rd power. But the unique wording here is, we could say this as 3 cubed. So that's the unique wording that goes along with whenever you have an exponent of 3. You could say 3 cubed. That also means 3, or whatever the value is, times itself 3 times. So the real meaning of 3 cubed, or 3 to the 3rd power, it's saying 3 times itself 3 times, so 3 times 3 times 3. So the real meaning here is 27. Go ahead and finish these last 2 rows on your own, and then we'll do more practice together on the next page.
Please finish the top of page 40 on your own, and then I'm going to walk you through the bottom of this page. So a lot of students struggle with more than and less than. So we're going to use a few examples because you probably use the words more than or less than pretty frequently. So if I say that Susie is 2 years older than Bobby, we have to think, okay, who is older? And I generally like to start off with a table. So I'm going to have Susie and I'm going to have Bobby. So S represents Susie's age and B represents Bobby's age. So if Susie is 2 years older, then we know that Susie is bigger or older than Bobby. So if Bobby is 2 years old, then Susie must be 4 years old. If Bobby is 3 years old, then Susie must be 5 years old. Basically, we are adding 2 to get to Susie's age. So we know that we're 2 years older than Bobby. So what that's saying is we're adding 2 to something, and that something is Bobby. Bobby's age plus 2 is, or will give us, Susie's age. And that's exactly what we found here in our table. So using these same numbers, if Bobby is 2, 2 plus 2 will give us Susie's age, or 4. So you'll notice is we took this sentence and we just rewrote it into a mathematical sentence using is as an equal sign and variables for our people. Okay, now Jenna is 20 pounds lighter than Chris. So if we look at the word lighter, 20 pounds lighter, we know that we're going to be subtracting 20 pounds, right? But 20 pounds lighter than Chris. A lot of students, and actually myself included, I get confused. Are we subtracting 20 from Jenna or are we subtracting 20 from Chris? Immediately, I go back to my table. We have Jenna and we have Chris. So Jenna is 20 pounds lighter than Chris. So I'm thinking already Jenna is smaller. So if Chris is 40 pounds and Jenna is 20 pounds lighter, that means Jenna will be 20 pounds. If Chris is 60 pounds, then that means Jenna is 20 pounds lighter at 40 pounds. Now that I see what's happening, I notice that whatever Chris's weight is, to get to Jenna's weight, I am subtracting 20 from his weight. So 20 pounds lighter than Chris gives us Jenna's weight. Hopefully you're seeing a pattern now. If we say Jenna is, we're talking about Jenna, represented by J, and then that is an equal sign again. So for this, let's do a check and see if it makes sense. Jenna is 20 pounds lighter than Chris. Jenna is 20 pounds lighter than Chris. So we're subtracting 20, but we have to subtract 20 from something. And we put our variables correctly because I checked my work with this table. Okay. Go ahead and try 3 on your own. And when you have your equation, hit play so you can see if we agree. So here, we're talking about David. We're saying that David received, or his score, D represents David's percentage, is 2% less than Sarah's percent. Let's go ahead and do a quick check with the table. If Sarah got a 90%, then David got 2% lower, so 90 minus 2, we would get 88. That does make sense. Now, let's see if we did something like this. D equals 2 minus S. Let's see if there's an issue with that. So if Sarah got a 90%, and we substitute that in, we see that David here got a negative 88%. Now, is negative 88 just 2% lower than 90? The answer is no, it is not. It is much lower. So the placement of your variable and this less than or greater than is very important. And we'll get to that with the next examples.
I think we should finish these two, have some fun on number 5. Are there any key points we want to make sure we include here? We can also be like, hey, put your own, put what you think are the key points.
Yeah, the whole thing was like, if you're saying you're smarter than or louder than or something, it's like there's got to be someone that you're taking away or putting towards. You know what I mean?
You want to put that in, you're smarter than somebody, like you're comparing with somebody?
Yeah.
Like than implies there has to be a comparison.
Yeah.
Or you can finish number 4 on your own.
Finish number 4 on your own. We just really want this right here. Sorry. Go ahead and finish number 4 on your own. We want these examples to help you realize that when you're older than, or right over here, smarter than, or smaller than, it's always compared to something or someone. So when we're subtracting 20, it's from someone. When we're subtracting this 2%, it's from something. So this placement of negative 2 or negative 20 or positive 2 is very strategic.
We're on page 41 here. Those vocab words you are responsible for. You can find them throughout your other notes packets. We'll also uncover them as we go through these examples. The one that I'll make sure you're aware of, the word of implies multiplication. Now, please don't think that forever and always when you read the word of, you're always going to multiply. It's not always the case, but you'll see in a lot of these examples that when you read the word of, it oftentimes means you're going to multiply what comes next. And we'll show that through some annotations and examples 1, 2, and 3. the rest of the vocab, you are responsible for having not just some definition, but the exact definition. So if you don't know it, look it up.
Okay. So example 1 says 9 more than a number. So if we're thinking, what does more mean? Well, more implies greater or addition. And it's 9 more and specifically. So 9 more than who? This then says that we are adding 9 to something. So we are adding 9 to a number n. N is the starting point, and we are adding 9 to it. Many students do 9 plus n, but then they're saying that we are starting with 9 and we are adding, or it is, I can't explain it
that was
now.
perfect.
I can't explain, I'm having trouble.
No, you're saying like 9 and then it's like being increased by n, but that's not what the sentence says. The sentence says 9 more than your starting point n.
Yeah. I like where you said
You're doing great.
this is great. Sorry.
Just pick up with like a lot of students do this.
Oh. Your editing abilities are insane. If you can get this to work.
We've been filming for 36 minutes. We gotta hurry.
Okay. So again, we have a starting point, and that number is n, and we are adding 9 to it. Now, a lot of students make the mistake of doing 9 plus n. But what that's saying is that it is n more than 9, making 9 our starting point, which is not the case.
We're here with example 2. I'm going to do a lot of annotating because there is a whole lot going on in this example. Saying the product, right away I'm going to stop and put a dot. The product implies we're going to multiply. That dot reminds me that I'm going to multiply. You also can, if you want to use the actual like multiplication symbol, you're welcome to. We try to avoid doing that because we use x as a variable so often in Algebra 1 that it can get confusing. So that's why I'm going to leave it as just a dot. So the product implies multiplication. Now of, as we mentioned, also implies, so we're going to be multiplying. When you read the product of, you should be expecting 2 or more quantities to come next that you're going to multiply together. So the product of, I like to put parentheses just to let myself know like whatever is going to come next, like the next thing, and the quantity afterward, I'm going to multiply together. So it's saying the product of 4 and m. So that's what I'm going to multiply together. It's saying I'm going to multiply 4 and m. If I had 4 times m, well, I don't know the value of m, so I can just keep them together. It's going to be 4m. So the product of 4m, now this is really important. It's saying all brought to the third power. So that implies I'm going to raise it to the power of 3. But notice how it said all brought. It's saying I'm taking this entire quantity, which we already established is 4m. I'm raising all of that to the third power. So it's going to be 4m, that whole quantity, to the third power. Now what a lot of students do, and again, like, understandably, they do 4m and then put a 3 right here. The problem with that is it's not what this sentence is saying. We're trying to mathematically recreate this English sentence and a mathematical sentence or phrase. This is saying 4 and then times m to the third. Right now this is just having this variable being raised to the third power. But that's not what the sentence is saying. The sentence is focusing on how this entire product has to be raised to the third power. This doesn't say that, but when you put parentheses around that entire product, that does now say what the sentence is trying to say. And we'll see the difference now in example 3. Example 3 looks really similar. It's saying the product of, so again, I read product. I'll put a dot to remind myself I'm going to multiply. The product of 4 and m. So I'm still multiplying 4 and m. That gives us 4m. And now to the third power. Because it doesn't say I have to take all of that to the third power, I'm going to have 4 times m, and now just that last part to the third power. You see a very important but subtle difference, because if I were to plug in like 3 for m, if I were to multiply 3 and 4, I get 12. 12 to the third power is a super different result from 4 times and then 2 to the third power here. You actually get different values. So while it might not look really important, mathematically it makes a huge bit of difference. So notice how because it didn't say all here, I'm just taking that last part and raising that to the third power. The last two examples we're going to go through together are just 5 and 6 because they show the importance of establishing a starting value and making sure you're actually recreating algebraically what the sentence is saying. So example 5 says the difference. Right away I'm going to pause there. Difference implies subtraction. So I'm annotating and making a note to myself, though I'm going to subtract at some point in time. The difference of, now if you put a dot for multiplication, you didn't really read the sentence. It's saying the difference of can also just implies whatever comes next. That's why we don't want you to memorize like of means multiply. It's not always the case. It can mean that, but it's not always the case. So the difference, subtracting of 7 and y cubed. Whenever you read the word difference, it's just implying that what comes next, that is your starting value. So 7 is our starting value. The difference of 7, I start here, and y cubed, which is going to be that variable raised to the third power. So let's have 7 minus y cubed. Because difference, there's no rearranging of the order. But as we look at example 6, it's saying 9 less than the number r. Okay. So it's saying less than, so that doesn't mean subtraction. So I am going to subtract at some point in time in this expression, or in this sentence. But again, let's think really carefully, and you might want to refer back to one of our first examples. What is your starting value? It's saying 9 less than this number r. So that's serving as our starting value. We're starting at r, and we're saying 9 less than that value. So we have r minus 9. This would also be a great time that if you're confused on this, make a table. So let's say we have some value r. Let's say r is 10. We're saying 9 less than that. Well, you all know that that's going to result in 10 minus 9, which is 1. So 9 less than that value. What a lot of students do is they have 9 minus r. They make this mistake. If we were to check this and like substitute, this would be saying 9 minus 10, which would be negative 1. That doesn't tell the same story that this sentence is trying to get at. It's saying 9 less than our starting value, which is r. Which is why r minus 9 is the right way to represent that same idea, but algebraically.